Hello class. Um, Today's lecture is 12.7 from section 12.7 and we will talk about the normal and tangential component. This is part of the curvilinear motion. So we will learn a new coordinate system that will help us solve particular questions that involve motion of particles about curvilinear path. So the objective is to learn what is the tangential and normal component, how to find the velocity and acceleration of a particle traveling along curved path. We will learn how to derive the normal and tangential components and what's the relationship between them. And also we'll take some examples. Examples where you can find the tangential and normal component analysis is useful is when you study car traveling along a clover leaf. For example, if a car is traveling, you will feel that while you are speeding about this curvilinear motion, you will feel some forces is attracting you to the center of that curve. The question could be, can you calculate the acceleration that resulted from this motion, the acceleration that is described by the rate of change of the velocity along the path, and also the acceleration that attracts you toward the center of that curvature? Another example is the swinging. If you have a boy swings as shown in this figure, and let's assume that the Cartesian coordinate system, which we all know now, described by the rectangular axes x and y, has moved and attached to the bottom of that boy and reoriented where the tangential component is tangent to the path of the motion and the normal component is going along the ropes. The question could be, similarly, can you find the maximum acceleration that the boy would feel, and where is it located at? How would that boy feel the acceleration as he's swinging from left to right, and or as the angle is changing? The angle that is measured between the vertical line and also the rope or the normal direction. The normal and tangential components plays a major role in the design. In roller coaster, the curvilinear equation of the roller coaster rail itself has to be carefully calculated and designed in such a way that person who is riding a cart wouldn't feel a lot of G's as a result of that cart moving from 2 points. The reason why, for safety, and also you want to make sure that this person are not ejected at any point. And you will be wondering what would be the maximum G's that person feels and at what location, and how would you reduce that G's? Of course, you will think about calculating the normal force that person will feel, and also you'll think about the tangential G's or forces that person will feel as they are sliding along the path S. So these two terms, we'll find them easily calculated using the normal and tangential analysis instead of using the x and y, which is, as we know, it's fixed and not moving with the particle. Alright, so let's go into the definition of the normal and tangential component. Assume we have a particle P sliding along a curvilinear path, and that position of the particle S is measured. Now, I'm interested to what I want to do is define two coordinate systems orthogonal to each other, or two axes orthogonal to each other. One is tangent to the path. I'm gonna call it tangent, and its direction is along the rate of change of that particle motion. And the second one is normal, as pointing to the concave. This is a concave, and it's pointing to the concave or to the center of that concave. So this is the center of that curve, which we defined as, if you would assume this is a complete circle, and this is going to be the center of that circle, and the n is passing through that center. So having these two orthogonal axes moving with the particle p will help us decompose their velocities and acceleration along these two axes. Now, as we know, the velocity of a particle, v, I'm going to call it v tangential, simply because the velocity is defined the rate of change of the position with respect to time. So it is the ds over dt, and if it's a vector, then it's in the direction of the tangent. And I'm going to call also this is u of t. So this is a unit vector, u of t, that has a magnitude 1 and direction is tangent to the path at that instant. Similarly, the un is a unit vector that is normal to the tangent and passing through the center of the curvature. Now, because the velocity, as we know, is always tangent to the path, the position path, we don't have any component for the velocity along the normal. To calculate the acceleration of that particle A simply is the derivative of the velocity, which is, we agreed, is ds over dt ut. I'm going to call the velocity magnitude, which is the speed, which was ds over dt, or s dot, or an equivalent, or you're gonna call it v without any vector space, so this is a v. So all of them represent the same. So instead of writing the velocity tangential in that form, I can write it as a v, which we know it's ds over dt, or s dot ut, right? So my a can be simply written by d over dt v u of t, and that is equal to d over dt v multiplied by u of t plus v d of ut over dt. Now, as you can see, this represents the component of the acceleration along the tangent, and this is the rate of change of the velocity magnitude. So simply this is v dot u of t plus v. This represents the rate of change of the direction, and by conducting some steps which I'm not showing here, this is equal to v over rho, where rho is called radius of curvature. radius of curvature, which will be equal, and this is, I'm sorry, I forgot, un, the direction of un. Okay, this is equal to v dot ut plus v square rho un, where this is tangential and this is normal. This is normal direction and this is tangential direction. So this is rate of change of the speed magnitude. This v square over rho is giving you the rate of change of the direction of that speed vector, or of the velocity, which will give you v square over rho and in the normal direction. So an, so this is a, so I can write this as at in the direction of ut plus an in direction of un, where at equal to v dot, or as double dot, right, which is ds square over dt square, and an equal to velocity square over rho. Okay, or speed square over rho. This is called normal, or normal acceleration, or centripetal component, always directed toward the center of curvature. Center of curvature. Okay. Now the magnitude of the acceleration is equal to at square plus an square, right? That's the magnitude. In summary, we have a velocity vector can be decomposed into normal and tangential, where it's equal to the speed multiplied by, or in the direction of, the tangential, and this represents the rate of change of the rate of change of the position. The acceleration is equal to the rate of change of the magnitude of the velocity in the tangential component, plus the rate of change of the velocity direction directed toward the normal, where rho is the radius of the curvature measured from the particle to the center of that curvature. Now, when the acceleration component in t is constant, which mean at is a constant, right? So what's gonna happen? So this means that s double dot is constant. So this is similar to the projectile motion, except that the acceleration is not negative g, but a magnitude. So let's say that this magnitude is at. So in this case, you can apply the kinematic equation of motion for a particle undergoing constant acceleration, where s equal to s naught plus v naught t plus half at, and again this is a constant, t square. You can also apply the second one, at a constant value multiplied by t, and also you can combine these two equations to arrive at one without any time and involve only the acceleration, velocity, and distance. And this will be useful along the tangential component. So looking back here, so the analysis involve knowing how far this particle will go along the path, the time it takes to go from one point to another, including that at is constant. The last note I would like to talk about before we start taking examples is how to calculate the radius of curvature, rho. Let's say we have a function which is given as a function of x, y equal f of x, such as x and y, and you have this function, right? And I'm interested to calculate the radius of curvature at this location, x star. I want to find rho, right? Okay, and this is y star. So find rho at x star, y star, right? Find it here. So there is a relationship that you can use, is that rho equal 1 plus dy over dx calculated at x star, y star, and that is to the power 3 over 2 divided over the second derivative, and this is again calculated at x star, y star. So that will give you the rho, which you will be using in the analysis. Let's take this example. We have a car travels along the road with a speed of velocity is equal 2 times s meter per second, where s is in meter, and s is measured from this location up until where it's at right now. Now, given the geometry or the radius of curvature is 50, because it's partially a circle, we want to find the magnitude of the car's acceleration at, and when it's traveled 10 meter, s equal to 10 meter. Okay, so the first step is to sketch the problem. So we have this particle or car and going along this path. It travels, this path is a circle that has a radius of curvature equal to 50 meter, which is the radius of a circle. We want the car travel 10 meter distance. There is a relation between the velocity, so the given to us is the velocity equal 2s meter per second, given. Find, well, the first thing, the magnitude of the car acceleration. So they want the magnitude of the car acceleration, which we know is equal to the summation of the squares of their component under square root at s equal to 10 meter. Okay, so the first thing we said, okay, I need to know AT and AN, and I'm given V equal to S. So we'll start with that. And now AT equal dV over dt, as we know, and that's equal d over dt of this magnitude. Now this is not function of time, so I need to rewrite it so that I can take the derivative. So I will use the chain rule, equal d over ds, okay, and this is ds over dt. And now, because of that, I can now take the derivative of d2s, and ds over dt is already, we know what is the velocity. So this is equal to the velocity dv over ds, and equal, what's the velocity? Velocity is already equal to 2s, and dv over ds is the derivative of that, which is 2. So this is equal to 4s, and the unit is meter per second square. So at at s equal to 10 meter is going to be equal to 4 by 10, and that is equal 40 meter per second square. Just want to make sure that you guys understand, when I plug this in, I just want to show you that I cannot take the derivative of 2s with respect to time, so I have to use chain rule. So this is chain rule, so you have to use that. Alright, okay, so we got the first one. What about the second one? And we need to find an at s equal to 10. Now we know an equal to v squared over rho, and this is equal to, and this is all calculated at s equal to 10, and v is 2s squared over and rho at s equal to 10. Now s is 10, so 2 multiplied by 10 square over rho is 50, and that's going to be equal 200 square, 20 square over 50, and the an will be equal to 400 over 50, and this is, I believe, 8 meter per second square. So we have an and we have at. So therefore a magnitude simply is 40 square plus 80 square, and that is gonna be 40.8 meter per second square. Let's take another example. We have a boat travels around circular path, and that circular path has a radius of curvature 40 meter at the speed that increases with time. Now this time we have the velocity is expressed as a function of time, and it's given by 0.0625 t square meter per second. Now we want to find the magnitudes of the boat's velocity and acceleration at the instant t equal to 10 seconds. Okay, so I'm gonna sketch first. Step number 1 is sketch the problem and label everything known and indicate what is unknown. So we have a boat, and this boat has a radius of curvature from O is equal to 40 meter. The velocity of that boat, or the speed, is given to us, given that the velocity which is tangential, as we said, always to the path. This is the path, or the S, call it, is equal to 0.0625 v or t squared. So it's a function of time, which is great. Now what we want to find is anything else given? No, that's all. So find the magnitude of the both velocity. So we want to find the magnitude of the velocity, and second, the magnitude of the acceleration. Okay, let's start with the first one. So I have to write, so I need to find the magnitude of the velocity, which is equal to, we know that the magnitude of the velocity is the speed. Velocity. I failed here to say at time equal to 10 seconds. So they want it at time equal to 10 seconds. So, which is the speed, right? And the speed is simply the evaluation of this speed. This is the speed at time equal to 10 meters per second. So that's as simple as that. Okay, so we solved the first one. Second one, we want to find the magnitude of the acceleration, which is always, we know, is equal to v dot square plus v square over rho square, right? That's what it is. These are the components. So at is v dot, and this is d over dt v, d over dt of 0.0625 t squared. So this is because this is both our time, so I can take the derivative, right? Multiplied by 2 multiplied by t evaluated at a time equal to 10. So this is at time equal to 10 seconds, simply equal to 2 by 0.0625 multiplied by time 10. This is going to be meter per second square. I'll give you the final answers. An at time equal to 10 equal the velocity square, which is 0.0625 square over rho. Rho is already 40, no, we know it, and that's going to be meter per second square. Now I failed here, multiplied by 10. Okay, so I'm going to rewrite this. An t equal to 10 0.0625 t square, 10 square coming from the v square over rho 40 meter per second square. Simplifying and calculating these numbers give you the speed magnitude is 6.25. You can try it at home. It's going to give you the tangential component at time equal to, let's say, at time equal to 10 to be 1.25 meter per second square, and the normal will be 0.9766 meter per second square. And from these two you can calculate the magnitude, and that's going to be 1.59 meter per second square. So with this we finish the normal and tangential. I posted already some homework. Please work on it. We'll meet next time in the lecture, and you guys have a good weekend.